We're going to start with just quadratics. I'm going to try to relate what we're doing today with what we've already done. That way it'll make more sense. It's an analogy going on here. So not too long ago, Algebra 1 and then again in Algebra 2 in probably October, we went over quadratics. Okay? And you were shown, hopefully, how different numbers do different things to the quadratic. A lot of different things. You can move things vertically, horizontally. Knowing what numbers do what opens up an awful lot. And eventually we'll be doing this with exponential functions as well. Where you don't have to make a t-chart so much. It's just know, well, this number is positive, so it's going to go this way. And this number is on the end is maybe a negative, so I know that the whole graph is going to be moved down when the number on the end is a negative, that sort of thing. And then we introduced the inverse of quadratics. Remember what that was? Okay. So we introduced the inverse. Okay. So what we did is we took something very basic, parabola, y equals x squared, and we said, let's find the inverse of this first by switching x and y. So we switched the two, x equals y squared. Then we solved for y so we could graph it. To solve for y, we had to take the square root. And technically, when you take the square root of both sides, you get plus or minus root x equals y. However, for our graphing purposes, since we wanted to graph a function, to keep it just a function, we only graph the positives. So that was called the inverse. Found the inverse of a quadratic equation, inverse of a parabola, and it turns out the inverse of a quadratic equation is a square root. Y equals the square root of x. Okay? And it looked like this. And it basically just looked like a parabola on its side. Okay? You can imagine if we did the plus and minus, not just the plus, it would look like a parabola that's just on its side. We went from here, and if you just rotate, we just rotate that, it looks like a parabola on its side. And it was a mirror image along the line y equals x. It was a mirror image right there. So what we're going to do today is do the same thing, but for power functions, exponential functions. We're going to take the inverse of what we did yesterday, and you're going to notice it's going to look like the same idea. It's going to look like it's on its side compared to what we did yesterday. So, however, it's not quite the same as just switching x and y and solving. Not quite the same. All right, so that's where we're going. Keep that in mind as we go along. Let's see here. A little warm up, sure. Okay, can we match these real fast? Which one is obvious and why? Okay, yep. 3 is obvious because it's, that's decay, right? So that's obvious because that's the only one that's going down. These are both going up. This is the only one going down. That's B. So remember, identifying growth and decay can really make a difference. Of course, if you're graphing it, you already know, okay, it's a fraction that's between 0 and 1. It's going to be going down. What about the other two? These look very similar, but what's different about them? The y intercept. So we're looking at this is a 2. This has a y-intercept of 1, and now it's easy to line them up. There's the y-intercept of 2. This one doesn't have a number, so it's like 1. Yeah, we can figure those out without having to plug in numbers and having graphing and talking about. Okay, so here's where we're going to go today. So we have such as the equation y equals 2bx. How do we find the inverse of that? That would look like the mirror image, just like a parabola and a square root function are mirror images. How do we take this equation, y equals 2 to the x power, switch x and y, and and solve for y. Same process. That going. Okay. Here we go. Take y equals b to the x. Notice how we're just leaving out the a right now. We're going to assume the y-intercept is 1. So we're going to have y equals b to the x. You switch x and y. Switch x and y. That's how I did from the first line and the second line. And now we need to get y equals. So how do you get y equals? We're introducing this new function, and you'll see it on your calculator. You've probably seen it a long time, and you always wondered, why does it say log? And that's what we're going to be using. We're using that button, log. It stands for logarithm, short for logarithm. Okay. So think of it as y equals x squared, okay, is to y equals square root of x. Okay. These are inverses of each other, as y equals b to the x as the log b to the x equals y. Okay. So the inverse of what we did yesterday is this new function called the logarithm, or log of x. Like we'd say the square root of x, it's the logarithm of x. It's the inverse. And when we graph it, that's when we get this graph. Okay. It's the mirror image along that line, y equals x. Same as it was the parabola and the inverse, or the square root. Parabola, square root, that mirror image. We get the same thing here. This is y equals 2 to the x. This one would be log of 2 to the x equals y, or y equals. Now, specifically, what does this log function do when you take the log of both sides? So the log of b to the y, and the base is b. Base is b on both of these. The log of b here, all of this just kind of cancels out. All that cancels out, and we get y. That's how we get the y left over. And on the other side, we're left with log b to the x. So it's like taking it's a function you can do to both sides. Take the log of both sides, take the square root of both sides, square both sides. It follows the same rules. You can do it to both sides, and you'll be learning a lot in the next few days how to do more with this, and why this works and how it works. The big thing to remember is that all these logarithms, the answer to a logarithm problem is an exponent. It's all about exponents. How can you figure out what the exponent equals? That's what we did here. We're trying to solve for y equals, which is an exponent. So how do you get y equals? How do you find out what the answer, what this exponent should be? Anytime you have an equation from now on, it could be anything. I'll just use numbers now. Like 2 to the 2x plus 3 plus 2. So, like an equation you guys did before, yesterday, they were the same base. That was pretty simple because all they had to do was set the exponents equal to each other. But what if they're not the same base? What if it was like something like that, not the same base? That's when you're going to start using this logarithm function. So that's what it is. That's when you use it. And the inverse of power functions or exponential functions are the logarithm function. Hopefully that clarifies what the logarithm function is. One of the first things you're going to be doing is converting. You're going to be rewriting something that's written in an exponential form into a logarithmic form. Because the log form we can know how to solve, but maybe the exponential we can't. So try to find the answer to again, I guess the big picture here is the answer to any logarithm problem is the exponent. That's the big answer. We're trying to find out what the exponent equals. That's why we use logarithms. We're trying to find the answer. What should this exponent be? What should that exponent be? The answer to a logarithm problem is the exponent. So here's something that's logarithm of base 4, 16 equals 2. What does this mean in the terms that we're familiar with? Well, maybe you can piece it together. Look at the numbers. How are they connected? Yeah, you guys can probably see it real fast here. Like, oh yeah, 4 to the second power equals 16. So it's just rewriting this basic thing that you already know in this new format, simply because once we don't know the exponent, then we'll be able to solve for it. So we can convert back and forth from exponential form to logarithmic form as needed. And we'll be doing that an awful lot. So we'll get really good at doing this. How about this? What does this mean? The base, 3 to the third power, negative third power equals 127. Same thing we already know, we just played this last time. And of course we can go the other direction as well. And let's do 5 to the third equals 125. Let's write that in logarithm form. There's the base. The base is the big number, right? So the log of base 5, 125, equals the exponent. The answer is always the exponent. These two things mean the same thing. Now, how we put those in the calculator is a little different. So we're going to talk a little bit more about that, I think, on Thursday. By default, in your calculator, when you hit the log button, by default, it's in base 10. So something like this, there is a way to put in your calculator, but by default, it's always base 10. So that's why you can't just punch it in right away and get an answer. If you start playing with things and trying to understand it tonight and tomorrow, and just know that's the case. We'll talk more about that later. All right. Good. More of the same. Why don't you guys practice these real fast? Just make sure you do it on your own. Small, but very important. This is one of those things that if you don't do right, it's like every single problem you might have to use this property, and then you can miss every problem just because you're not moving the numbers into the right place, and therefore you're not going to put it into the calculator correctly because the numbers are in the wrong place. So let's just understand this part first. There we go. Anybody got an answer? Yeah. Go ahead.
Log 4, 16, 4 equals
4 log. Oh, log. Sorry. Log of base 4 of 6. Okay.
That's like
Base 4, 64 equals 6. Another. It doesn't matter if we have fractions, negatives, or anything. We know we can have fraction exponents. We know we can have negative exponents. Don't let that bother you or change the steps on solving any of these. Got your answer? We want to give it a shot? Log of, yeah, log of 125 or log of base 125? Base 125. Okay. Of 5 equals always equals the exponent. Exponent is always the answer to a logarithm problem because that's what we're solving. If you have an equation and it says the x or the y, whatever you're solving for, is in the exponent, this is how you get the y equals or x equals. Solve for it. You got to get it out of the exponent and into regular solvable problem. And just for fun, let's practice this. I'll tell you how to solve for this. If you plug it in, type in log 64 in your calculator, divided by the log of 4. And that should give you 3. So if you want to actually verify these things, that's how you plug it in. This is called the change of base, which we'll explain later on. So technically, it makes both of these base 10, so we can just type it into the calculator. That's what we just did. There's a lot more to this, but I just want you guys to know how to use your calculators properly so you don't start using them wrong and then have to figure it out later. So same thing here. If you type in log of 5 divided by log of 125, you should get 1/3 or 0.3 repeating. And then in a few sections, you must have the calculator in order to do all these problems because they're going to be kind of like square roots where you might have the square root of 52 in the middle of the problem. You need to type in the calculator square root of 52 to get that decimal. You'll need to type in some of these logs just to get the decimals to know what to do next. So it's going to be a must to have a calculator. In the old days, they just had charts of these and tables of all the numbers in the back of the book. And you had to look in the back of the book and look up by me log of 72 and find out what the decimal is, and now we just use a calculator. So now we know how to go from the two different forms. If you're in logarithm form, we can change it back to the exponent. And if we're in exponent form, we can change it to logarithm form. We know how to use the calculator regardless of what form it's in. Maybe more. Okay. So even though we can use the calculator, can we figure this out without the calculator? What does this mean right here? Here's how you want to read it. When it says log base 3 of 81, here's what you need to be thinking. 3 to what power is 81?
4.
Okay. 3 to what power is 81? 4. Okay. That's the question. You want to be thinking in your head. You want to say this to yourself when you read this. 3 to what power is 81? Okay. That's what you're thinking. So yeah, calculating get the answer, but let's try to do it without. So for the easy ones. Obviously it's not perfect, then you'd use a calculator and get your decimals, but when it's kind of like knowing if I ask you what's 5 cubed, and you say 125. What's the square root of 144? 12. You want to know these numbers quickly without a calculator. Same thing here. When the numbers are nice, you want to be able to just get the answer pretty quickly. Sometimes they're not. Sometimes it's the square root of 117. Then you use a calculator. What's that? Let's try another one. So try this. So what does this mean? If you had to say it out loud, what does this mean? Yeah. 4 to what power is 256? So the question is, 4 to what power equals 256? That's what you're answering. So you got to figure out, is it 4 to the second power, 4 to the third power, 4 to the fourth power? What power is it? And quickly you come up with 4 again. Yeah. 4 to the fourth power equals 256. Or in your calculator, you can verify the log of 256 divided by the log of 4, and you'll get an answer of 4 as well. Okay. Yeah, it's kind of like trying to learn a new language. Kind of. What is the most popular use of logarithms? What is the most common use of logarithms? Okay. That would be something called the Richter scale. The Richter scale. So when you guys think of earthquakes, you think of how strong the earthquake is. That decimal, it's a 4.5, it's a 5.2. That's a logarithm. Okay, that's actually an exponent. Let's say if it's a 2.0, okay, that means it was, how strong was? It was 10 to the 2 power. Or the log of what equals 2? To the 2 power. Okay? And then if it's a 3.0, okay, it's 10 to the third power, or the logarithm equals 3. Okay? But the answer, how do you solve and get that strength? It comes from solving a logarithm equation. That's how they get, oh, it's a 2.0. Oh, it's a 2.7. That means when they solve this equation, okay, it comes out to 2.7, and the x is what comes out of the, all those spikes and everything from the machine. Okay? And it comes out to a 2.7. So every time you see or hear about an earthquake, okay, that's what it is. It's a logarithm. What else? So how much stronger is a 2.0 than a 3.0? Or a 3.0 than a 2.0? How much stronger is it? This is a way to really understand logarithms, is to understand this question. So you think from going from a 2.0 to a 3.0, you think, oh, that went up by 1. How much stronger is it? 10 times as strong. 10 times, because this is a base of 10. So how do you go from 10 to the 2 power, right, means 10 times 10. Right? 10 to the 3 power means 10 times 10 times 10. So how much stronger is this than this? Yeah, it's 10 times as strong. If I multiply this by 2, then I'll have to the third power. So a 2.0 or a 3.0 is 10 times stronger than a 2.0. And if you have like a 7.0 and like a 4.0, how much stronger is a 7.0 earthquake than a 10.0 earthquake? Yeah, 30 or, okay, so 4.0 would be 10 times 10 times 10 times 10. 7.0 would be 7 tens, right? So how much stronger is it? 1,000 times stronger. 3 more tens. So there's between 4 and 7, there's a difference of 3, but that's not 3 like 30, that's 3 tenths. 3 times 3 times 3. So it's 1,000 times stronger. And this is that's the most common use that you guys would understand for all this logarithm stuff. So when we talk about like an 8.0, that is like 10,000 times stronger, 10,000 times more shaking, 10,000 times more damage. Okay, it's not just it's 30 times as big or 3 times as big or just a little bigger. We're talking about factors of 10, way bigger. Okay. All right, good. Logarithms are just exponents. Remember, the answers to logarithms are exponents. We're taking y equals b to the x, and we're solving for x. How do you get x equals? Okay. Turns out you take the log of both sides. Take the log of both sides of base b, and then right here, the log of base b of b to the x. Okay. This b cancels out with log of base b, and you're left with x equals. Well, that's how it works. We're actually taking the log of both sides, kind of like with a quadratic, we took the square root of both sides. Same idea, just this new function we haven't used before. And that's about it. I'll let you guys get started because you might have questions on these, and just to get familiar, use your notes. We already did the homework. Yes. So let's practice converting. I will not be here tomorrow. I got to go to do a workshop thing to figure out Common Core stuff. So you will have just some review on graphing and some more basic logarithm things. Might throw in some stuff about earthquakes so you can practice understanding it. Yep.